Hi everyone, this is Lesson 6, Video 2 on work and efficiency. This video is dedicated towards giving you some worked examples of the types of problems you might see in our course. Before we go into the worked examples, we should do a little bit of revision on some of the terminology. Work, energy, efficiency, and power. Energy is the ability to do work, and in this first image of a trebuchet, we see that it is ready and waiting to do some work. It has gravitational potential energy stored within it, and it's ready to let fly. Work itself is the act of transforming energy from one type into another. In this second image, we see a trebuchet actually in the process of releasing its load. Gravitational potential energy has been transformed into kinetic energy. The stone will fly and hopefully hit the target. Efficiency is a human concept. It comes from the second law of thermodynamics, which tells us that no matter what happens, every single energy process will always result in the production of some heat. With efficiency, we're asking the question, to what degree are we successful in conducting the work that we wanted to do? We have an energy source, we do the work. The work we define as useful is what we wanted to achieve, and we compare that to the energy that was lost as heat. We compare that to the energy that was put in as our source energy. Power is a measure of the rate at which we're able to conduct work. Power is measured in watts, where 1 watt is 1 joule per second. Here's the first of our 4 examples for this video. An LED globe receives 360 joules of electrical energy over the course of a minute. If the globe emits 342 joules of light, calculate its efficiency. Okay. Remember, in all the other questions that I've done with you, we always look at a process that we like to follow. We like to highlight the important information from the text. We like to write down our givens. We like to declare to the examiner what we're going to do, put in our equations, do the calculations. In this question, we can see that the important information is 360 joules of electrical energy goes into the globe. 340 joules of light comes out of the globe, and we're being asked how efficient is the globe. Our givens are listed. Efficiency is equal to the work conducted that we wanted to do divided by the total energy submitted in, multiplied by 100. We plug in our values. We have efficiency is equal to 95%. That little N shape to the side there is a Greek letter eta, ETA, and it's the letter that we use to denote efficiency. Here's our second example. In a laboratory experiment, a 900-watt microwave was determined to be 72% efficient. How long would it take to heat 300 mils of water from 25 degrees to 65 degrees Celsius? What's the important information? Our microwave is a 900-watt microwave. That's a power rating, 900 watts. So it consumes 900 joules of electrical energy per second. That's important information. The microwave is 72% efficient. We've placed 300 mils of water in the microwave at 25 degrees Celsius. We want to raise it up to 65 degrees Celsius. So we need to know, how long is that going to take? Well, we're going to have to figure out how much energy is going to have to go into the water to achieve this. There's our givens: power, efficiency, mass, and the initial and final temperatures. This is where we're going to start the problem. The microwave is said to be 72% efficient, which means that 0.72 of the total energy given to the microwave is actually going to go into the water. 0.72 of the energy given to the microwave is going to go into the water. What's it going to do? It's going to raise the temperature of the water. So we're going to use MC delta T for that part of the calculation as we raise the temperature of the water. Now, here's the problem. We don't know the total energy going into the microwave. We just know the power rating on the microwave. However, because we know that power is work divided by time, we can say that energy, or work, because that's what we're trying to do here is work, is equal to power multiplied by time. Now we've got something we can work with. 0.72 of the energy going into the microwave heats the water. Well, the energy going in can be determined from power multiplied by time. And in the question we've been asked, what is the time? We know the power rating is 900 watts. We plug in all of our values, do a little bit of algebra, And we see that the time it takes to raise the water by 40 degrees Celsius is 77.4 seconds. Here's example number 3. A piston compresses a cylinder of gas doing 1,220 joules of work on the gas. During this compression, the gas loses 370 joules of energy to its surroundings. That's heat. What is the net change for the internal energy of the gas during this process? What's the important information? Let's highlight the question. The piston compresses the cylinder of gas. So the gas inside the cylinder is our system. When the piston compresses down onto the gas, the piston is doing work on the system. So that type of work is going to be positive on the system. During the compression, the gas loses 370 joules of energy. That's going to be heat that it's lost to its surroundings. We are supposed to figure out the net change for the internal energy of the gas during this process. Let's list our givens. Work is going to be positive 1,220 joules. Heat is going to be negative 370 joules. The work is positive because the work is being done on the system. The heat is negative because the heat is being loosed or released by the system. Our equation, delta U is equal to W plus Q. We plug in our values. The change in the internal energy of the system is 850 joules. Example 4, our last example for this video. A cylinder of gas does 970 joules of work on a piston. So the gas is the system. The gas has got internal energy within it. The gas is using the internal energy to do work on the piston by pushing it up. That's what the gas is doing. At the same time, the gas transfers 620 joules of energy to the piston and the outside system while it expands. So the expansion is the work, but then the gas is also releasing thermal energy to the piston into the outside world. This is heat. How much does the internal energy of the gas change during this expansion? We highlight the important information. The gas does work. The gas transfers or releases energy as heat. That's going to be negative. We list our givens, declare our equation, plug in our values, and we've got the answer. The change in the internal energy of our system is negative 1,590 joules. Right, that's the end of the video. So what now? Take a moment, shut down your computer, open up your textbook, jot down the ideas from the video as you can recall them right now. Try to do it from memory. Don't go back and just copy things out. When you're ready, maybe you should go and do those practice problems yourself without looking at the video. See if you can do them. Then use the video for help if you need to. Read and take notes in Chapter 2.1 of the Pearson Physics 11 text. Complete Chapter 2.1 Work and Efficiency questions from the Pearson Physics textbook. Complete the exit ticket for Lesson 6, Work and Efficiency. And I'll see you soon.